Hi, I'm Jay, DuoMark if you've on Twitter, or on GitHub I'm also DuoMark. And I'm going to talk about raw Erlang processes and how to make them talk to OTP, because everybody says use OTP, and OTP is gen servers and gen FSMs and supervisors and all these higher level concepts that are used to build architectures. But when you read Joe's book and you talk to some of the original programmers, I don't use any of that stuff. I just, gen up a receive loop and start playing from there.
I would like to add that I've never seen any of Joe's code actually in production.
This is a good point. This is a good point.
And to that, I'd also like to add that those who say, oh, we don't use OTP, usually regularly appear in the top 10 best programmers in Sweden who got all of the error cases which OTP handles in their mind when they're programming. So
I use OTP, I use GenServer, and I haven't really written much raw Erlang. Right from the beginning, I started using OTP. And I've used Erlang to challenge the concepts that I've accepted from 60s trade-offs, when you wrote to disk as infrequently as possible, and the costs of computing were decided early on, and databases and things like that were built around it. When I started using Erlang, I discovered that I could think about a problem in a very different way and a very different approach by using more processes. And so I started re-implementing some of the concepts that I was very familiar with, trying to do them in new ways. And one of the arguments early on was that if you're using Erlang, you've got thousands of processes, 3-4 orders of magnitude more processes than somebody who's using another language like Java or something else. And so your approach to the problem can be very different. Well, now on the horizon is 10,000 core CPUs. And so an Erlang programmer today might be capable of using, 100,000 to 1 million processes. If you have a 10,000 core CPU with enough RAM, you may have 10 billion processes. So 4 orders of magnitude more processes. You're now the Java programmer, if you write Erlang today, and you're being confronted with tomorrow's Erlang programmer who has 4 orders of magnitude more processes than you have. What would Erlang look like? How would you solve problems? Would you do them differently? And I've been playing around with a library that I'm working on that wastes processes as grossly as you can, because whatever's cheap, you just waste them and come up with a new solution. And in the process, I decided not to use gen events and gen servers and things like that, but to use core Erlang processes, but make them compatible with the existing OTP library so that I can slip in a new approach to programming side by side with existing OTP framework, and get the advantage of all the OTP tools to debug this code that's still being formed. And in the process, Jeff accidentally made the perfect lead-in, setting up with DBG and Erlang Trace and all that. I'm going to talk about proclub and sys, which I don't hear anybody talk about very often or at all. Proclub is for handling Erlang processes that are raw, but they're compatible with gen servers. And sys is for debugging and tracing OTP compliant software. So just first off, how many people here came because they wanted to learn about Erlang and see what it was about? And how many have been using it for a while? And how many have a lot of experience? So the people that are kind of getting new exposure to Erlang, okay, that's about half the crowd. And people who have used it for a little while but just kind of consider themselves middle-of-the-road practitioners. Here's a seasoned veteran up front raising his hand. Okay, and people who have been using it for 5 years or more. Okay, so this is mainly introductory. I'm going to start out very slowly down the road, about 5 miles an hour, and we'll get a few hundred yards down the road, and I'm going to take off at about 100 miles an hour and go a very shallow dive into a very deep subject of OTP that you don't really hear about. So I'm going to try and introduce some of the concepts of Erlang along the way. One of the things that I hear new people coming to Erlang say is that there's no tools, there's not enough tools, you can't see what's going on or use it. And it's mostly that they're not aware of all the tools that are available, because there's an enormous number of tools available inside Erlang. So a process. Everybody talks about Erlang processes and concurrency. What is a process in Erlang? You can't execute code unless you have a process. So if you write a function, you have to have a process that executes it. And each process has its own memory space. So they're completely independent. Another process can't see inside your memory space. You have to use message passing through an external interface to get data from one process to another process. Inside a process, execution happens serially. And in Erlang, unlike JVM and other things, there's not a multi-threaded garbage collector. There's a single thread garbage collector for every process. So garbage collection can be very fast because processes are small. The idea is not to write a big process, but to write a lot of little processes that do very particular tasks. And then you're not going to generate as much garbage. The garbage collector will run really fast. And you get the natural concurrency out of the cores and the VM doing the process switching for you. So to create a process, you use Spawn or SpawnLink or SpawnMonitor. There are three variants on the same thing. Spawn creates a process, sets up the memory space, starts execution on some function. SpawnLink lets you create a new process, but that process is going to be linked to the process that initiated it. And what it means to be linked is that you're connected for life. If the other process goes down, it's going to take you with it. Using the scuba diving analogy and pairs programming would be a good sign. If you have one diver sink, the other one's going down with. The nice thing about SpawnLink, as horrible as it sounds, is that it lets you manage a collection of related processes that are all essential to solve a problem. If I need a connection to the database, and I need a memory cache, and I need an interface, if any one of those fails and they're linked together, all of them go down, and then you can start up a fresh new initialized version of all three and know that it's going to work again. So it's a way to manage a group of processes that are related to each other without having to give them names and do all kinds of arbitrary management things to keep track of them. SpawnMonitor is when two related services need to be aware of whether the service is available or not, but it's not a hard failure if the service is down. If I'm going to go on the internet and get information, but I also have stale information locally, and I'm aware that the internet service interface is down, then I can use my stale information locally and continue operating normally. And that's how you get a fault-tolerant kind of behavior. You either take out failed required processes through the linkage technique, or you use monitoring to say, well, this service isn't available right now. Later on, it may become available, and then I'll be aware of it. I can use it. When I create a new process, I get my new empty memory space. I also get a special thing called a process dictionary, which Jeff talked about. It's a key value store that you're told never to use. Because it leads to imperative style programming where you store something in based on the key, and then you might change it and get it back. The main reason why they say don't use it is because if you're doing anything in the process dictionary, it stays there for a long time. And your code may make an assumption, because it's functional code, that every time you run the function, it's going to work the same way. But if it's dependent on accessing a value in the process dictionary, and that value can change, the function will change its behavior when you run it at different times. If you're implementing a reflective system, or a system that needs a management of its processes, or a system that's going to keep track of historical information over the course of a month and then suddenly go wrong, and you need to find out what may have gone wrong, you need some sort of long-term storage that you can rely on. And a process dictionary is the perfect thing to store little snippets of metadata that are about this process. So if this process is still around, I can find out the metadata. If it goes down, the metadata is gone. That's fine. Once you start execution, the passed in function is what's going to run. And you get back a PID the thing that Jeff had trouble pasting into his shell. The other trick to getting a PID, if a PID prints out on your shell, there's a thing called V in the shell, which tells you the value for one of the previous commands. And you can get the value of the last command, which is the actual PID itself, and then you don't have to paste it. But that PID is the unique identifier, which is supposed to be unguessable. Lots of times in Erlang code, you'll find people registering PIDs and giving names to things when they create them so that they can have loosely coupled code and reference it by name. But ideally, you don't want to use naming very often because it leads to bottlenecks in serialization going through the name server and assuming that there is one thing with that name out there. So to the extent that you can pass around PIDs and use PIDs, you can have a more peer-to-peer type architecture. I'm going to give an example here where I'm spawning a process. I'm just going to spawn a process and look in the dictionary to show that there is a dictionary and that it's empty when it starts up, to show you I've set up a new memory space that's empty and I'm running my function. So I just write a function called getDict. It uses the process info. I think James was talking about that, but also Jeff. All I do is log the entire dictionary. And you can see when I start up, I'm calling spawn with the module name and the function name and the arguments that get passed in initially. And my error logger prints out that I've got an empty dictionary and it returns a PID there. I can also use a fun, which is maybe not a good thing to do. If you're doing code upgrade, it's very difficult to code upgrade a fun because it's just kind of out there. It's code that you've injected into your system and now it has no name, no reference, and it's hard to upgrade unless you put all the functions that you need to do upgrade. And I'm going to talk a little bit later about how you make it possible to upgrade with a function, with a raw process. So here I've done the same thing, just using a fun rather than a compiled module function. So now once you have processes, they have their own memory space. They have to communicate to get any data transferred or to do any processing. So sending a message, you can use bang, which will send the message to the PID or to a name if you've registered it, and Erlang send, which is in the Erlang module. That one has some extra options that you can use. Those are mostly related to distributed Erlang. In distributed Erlang, if you bring up 2 VM nodes, they'll automatically connect by default. And sometimes you may want to not have them automatically connect. And you may want to send a message. Normally sending a message says, hey, wake this guy up and make sure he's part of the node network, the mesh network. Sometimes you want to send a message and say, don't connect to the rest of the nodes. That's what the Erlang send would be used for. But in most code, you'll just see bang, the exclamation point operator. What happens with an Erlang process is there's a message mailbox, and there's one mailbox for every process. So you've got your empty memory space, you've got your process dictionary, and now you've got this mailbox. Messages are delivered to the mailbox just in the order that they're received by that process. Another process sends it. If it arrives, it locks the box, puts it in, and then returns to the next step in the sending process. The order of the messages in the mailbox are going to be the order that they arrived, and they stay in that order. But there are operations that let you receive not just the next message, but you can selectively choose which of the messages based on pattern matching. This is what makes Erlang really nice. Pattern matching, everybody talks about it. What it does is intrinsic to the language, it lets you describe a data structure based on its shape, or that it has a tuple with 3 elements, or that it's tagged with a certain value. So I can run through my mailbox and pull out only the important messages and leave all the other ones there. You're guaranteed that if process A is sending to process B, and it sends 3 messages, if the 3 messages arrive, they're going to be in the order that they were sent, unless they go through a third process. Because that third process could be you know, in Antarctica and be remotely sent back to you, and it may take a while. That's generally considered a drawback, but it's actually an advantage. Sometimes you may want the messages to be in a different order, and you can use a middleman process to do that. So here's an example of receiving messages from my mailbox. So I've got 5 or 10 messages in my mailbox, if I'm following Jeff's administration principles. In my receive, on the left side, I have a pattern which will match any data structure. It's just a variable that's unbound. Anything that's in the mailbox, the very first thing in the mailbox is checked, and it matches. I then call the function handle, passing in the message that I got out of the mailbox. And with this code in this receive loop, I would just be able to run through, if I looped, I would be able to run through the mailbox and handle them in order, doing them one after another. It will dequeue the messages and do a synchronous handle on each one. But sometimes I want to just get some of the messages out of the mailbox and leave the rest there. So in this case, I'm matching on a pattern, which is a tuple of 2 elements. The first is a tag, that's the message type that I'm looking for. And then the second argument in the tuple is an unbound variable, so it'll match whatever is in the message. And now I can call the handle my way, and I've left off the data element, but I would be passing the data element to that handle my way. And in this case, I've added a clause. After 100 milliseconds, I'm essentially returning the atom continue, so I do nothing. So if I were to call a function that had this clause in it, it would find a my message, handle it, but if after 100 milliseconds it didn't find any, it would return. And it will look at the first message in the mailbox. If it doesn't match the pattern, it'll go to the next, the next, the next. It'll linearly scan down and pull out. So that's how you can do selective receive. So now that's raw Erlang, spawning a process, message handling, why you use processes. When you have OTP, you get these new things, gen servers, gen FSM, supervisors. There's a bunch of objects. They're built on top of processes because code can't run without a process. But what they do is they follow a set of rules so that as a collection in an architecture, you can do things like Jeff was doing, suspend processing, which means allow messages to arrive at my process, but don't do my receive. Don't pull any messages off the queue. And then when I say resume, now you can start pulling messages off the queue again. That's a system admin thing. As long as the architecture follows the principles and follows the standards, then you can apply these tools to any of your processes. And if you use gen server, gen FSM, and so on, you automatically get all those features, and so you don't have to do anything special. But what you do when you use a gen server is you buy into the approach that OTP is using, which is a push approach. I no longer use receive and do my own pattern matching. I actually call API functions. I mean, I implement API functions which are automatically called on me when messages arrive. So essentially, a message comes to the mailbox, it's in the receive loop, and the receive loop is handled by OTP. And when it recognizes the pattern, it pushes out by calling my API function. So it's almost, in a sense, like Node.js doing callbacks on your module. But what it gives you is the ability to have asynchronous messaging and synchronous messaging. So you don't have to implement that. If you were using a receive loop, you would have to actually do the receive and then do the ACK and manage synchronous messaging yourself. You can do sync, async, you can get TCP raw data as info messages. Those are all built in. But it also builds in code change and cleanup that happens on termination. Those are things that are built in that don't happen in raw processes. The other thing you get is supervisors. Supervisor is an Erlang concept where you make a hierarchy of processes that are presumably related to each other. So if you had a service that connects to the internet that requires 10 processes to manage all the interaction with the internet, you might hook those up in a supervisor hierarchy so that if one piece of it fails, the supervisor can restart that piece. And that's another fault-tolerant behavior that they have, is that failures can happen. Like James had failures happening, and he didn't even realize it until a month or two later when he looked in the log file. The supervisor was restarting the process. It starts out clean at an init with a brand new memory space and process dictionary and everything, so there's no issues lingering from the previous problem, unless you have a hardware failure, in which case repeated failures will take out the supervisor and work its way up the tree until the whole node comes down or transfers you to another node. The basic thing, though, is that supervisors have a mechanism for communicating with their workers, and if you want to have a raw process that can be managed by a supervisor, you have to follow those rules as well. So what are the requirements to be OTP compatible? There's basically 4 requirements. It's kind of messy if you go through the documentation to figure out exactly what all the requirements are, but these are probably the 4 main ones that you would need. You want to use proclub to spawn your processes. That's a module that's part of OTP. It comes with your installation. I'll explain a little bit what it does. Then you have to be able to handle system messages. All the tools that Jeff was using generate system messages which are sent to all the processes and components in your system. And if you don't handle a system message, you'll receive a message, and depending on how you wrote your message handling, it may either hang because it's a message sitting there that you have no handler for, or it may just skip over it and it ends up in your mailbox, and eventually it shows up on his list of one of those processes with thousands of messages in it. And those are plain system messages. It turns out debug messages also go through system, but the message itself has a debug tag on it, so you can differentiate the two.
So there's a difference between the ERTS debug tracing stuff and the sys-level debug
Yeah.
stuff.
So
They're not quite the same mechanism.
ERTS is an Erlang runtime system, and that's what has the VM and the Erlang module with the BIFs, the built-in functions. And there's a function, Erlang trace and Erlang trace patterns. There's a bunch of tracing functions that are in there. And those actually hook into the instrumentation of the VM. And the VM has hooks that call out at a very low level, and the BIFs are aware of them. And so if you call a function, the BIFs know that that function was called. If you turn on a tracing for that pattern, it will send messages with that information. Sys is a module that was implemented at a higher level as a system administration tool to generate debug messages and trace messages. And you can create your own debug and trace messages, and you can call anything, and you can call the Erlang, low-level ERT stuff. You could call NIFs, you could do whatever you want, but you kind of have to sprinkle in your own code, whereas when you use the Erlang stuff, the code's already sprinkled into the VM. So this gives you more control. It's mostly for implementing a library, I would say, because you're trying to debug a library rather than a production system. You have the freedom to sprinkle these things in. The last thing you have to be able to do is respond properly to a shutdown message. If you have a linked process and it goes down, you're down. The VM takes you down. But if you don't want to go down, yet you still want to know that that link went down, you can trap exits. And when you trap exits, that means it won't take you down. It'll send you a message that says, I was going to take you down. If you didn't have that trap exit set up, I would have. So do something about this exit. If a supervisor sends you a message to exit, that means the supervisor is trying to shut down, and it's trying to shut down all its children. You better shut down, and you should pass the reason that it gave you as the reason why you're shutting down. That way the supervisor knows that it wasn't a normal shutdown, and it will try and restart you. If you don't handle this properly, then the supervisor won't be able to restart your process. So proclub. Proclub is just for creating things. And early on I heard, don't use spawn, use proclub spawn, then it'll be compatible. So you sprinkle proclub spawn everywhere you did a spawn, which hopefully wasn't too many places because you were doing gen server start link on all your processes. And then you never did anything else, and you never saw any benefit, and you never saw any value of it, and you had no idea why you were doing this. Turns out what proclub does is it keeps track of how you started the process, what function did you call, and who the ancestors were. What was the parent that spawned that process? And that's basically all it does. Sys is for controlling and debugging, and as Jeff showed at the ERTS level, Erlang is for tracing, and I'm not going to talk anymore about the VM level stuff. In proclub, instead of doing spawn F1, now I'm doing proclub spawn F1, and lo and behold, my dictionary pops out and it's got values in it. I thought when I spawned a process, the dictionary was empty. It was. Proclub spawned it, and then it immediately inserted who was the calling process, the PID, and gave that the ancestors label. And it put the initial call in. And since I was doing a fun, I get this very helpful Earl eval expr 5f fun one. If I had used a module and a function compiled, I would have the module name and the function name there. Now it turns out it doesn't give you all the arguments back because your argument might have been that crash dump file that he had that was 18 gigabytes. And if that was sitting in your process dictionary, you would be able to spawn like 2 processes and then you'd be done. So it cleans up the arguments and tells you, oh, you had 4 arguments when you called this. But if the main thing that proclub does is when you crash a raw process that was spawned with proclub, it can give you a little traceback and say, hey, it was called by this and you called it with this initial function. If you crash a regular Erlang process, you get nothing. It'll just silently disappear and you won't know why. Proclubs generally silently disappear too because you've just spawned them off in the distance and they're not communicating back to your shell. So it's not enough just to use a proclub. You kind of have to be aware of what it's doing and why it's doing it. The one thing that does happen, if this proclub that I spawned then spawned another proclub, the second proclub's process would have an ancestor pushed on the front of the list. So it actually keeps a chain from the original parent all the way through the successive spawns. And that's related to the supervisor hierarchy. But it also gives you a trace of how did this process get spawned from all the parents that got you there. Proclub's pretty simple. It has a bunch of API calls, and you go look in the code. It's not that big. It has one hidden little gem that you'll probably never find in anybody's code, that you can hibernate a process. So you could spawn a proclub process, and you could hibernate it using proclub hibernate. I've never seen that in anybody's code. Well, I think Ulf Wigger had put it in plain FSM, but that's about. I'm sure that in the telephone companies, there's places where that code is, but it's pretty rare. It turns out that Erlang has a function called hibernate, which is for saving memory and putting processes to sleep. Because if you make 1 million processes and only 20 of them are receiving messages, or even 1,000 of them are receiving messages, the others are just wasting memory and sitting around. If you could shrink them down and put them away like they were zipped up because they're not going to get a message for minutes or hours, that would save you a lot of performance. And that's what hibernate does. It's in the ERTS, it's in the Erlang BIFs. What it does is it kills your code stack completely, and then it garbage collects the process. And then it looks at how much memory is left, and it shrinks your process to the exact size of the amount of memory needed for the data. And when you run your VM, you can actually specify the minimum stack size, the minimum size that you want a process to be, because you may not want it to allocate memory by a little bit and more and more and more. So you may set, I need this much memory, it'll run, the garbage collector will never run, and then the process dies. Hibernate can actually set your process size smaller than the minimum size that you've specified when you spawn things. But as soon as you get a message to that process, it's going to wake it up, it's going to zoom it up to the minimum memory size, then it's going to look at the message, and it might just say, oh, this is a system debug message? Okay. And it's not for me? Toss it. Okay, hibernate, shrink, put me aside again. The big deal, though, is that it actually throws away your code stack. So one thing that proclub does for you is really nice. It wraps a trycatch around the function that you invoked. When I did a spawn with a fun, It just executes the function. But when I do proclub spawn, there's a trycatch wrapped around it. And if it ever fails for any reason, it prints a nice crash report with my ancestors and what was my initial call. And that's how it works. It gets it from the process dictionary. But if I hibernate the process, it throws away the trycatch block. It throws away the entire code stack. And so now if I were to resume, I wouldn't get that nice crash trace. So proclub hibernate puts the trycatch back around the code before it executes so that you'll still get a crash. And this is how you would invoke hibernate on a process. Now, who would ever do like thousands of proclubs and then say, oh, my proclubs are too small, I need to hibernate them? That's why it's not used very much. But people do lots of gen servers, and at some point the gen servers, the states got big and everything, or the garbage collection hadn't run in a long time. Hibernating a gen server was a thing that really saved space, and so it had to be added at the bottom for the VM, and it had to be added to gen server. Putting it in proclub minute worked on all of OTP. So now Jeff had this really cute trick where he did the suspend and resume. It's jumping through hoops. How do you do that? It's kind of tricky, but what you have is a receive loop. Here's an example where I have a receive loop. I'm handling my messages, but I might receive a message that says, why don't you pause for a few seconds before you resume handling messages again? So just as a simple example to show you in raw Erlang how you do that, in my loop I receive, if I get a pause, I call the function wait with the amount of time to wait. If I don't, I handle the message the way I normally would. So the pause goes to the back of the queue, I handle messages. As soon as I get to the pause, it matches, it jumps to wait, and I do a receive, and after that amount of time, I just call loop again. So it's almost like a coroutine. I've stepped aside outside of my receive loop, and I wait there and twiddle my thumbs, and then I jump back in to the loop function at the top. So this is how sys essentially works. Uh-oh, running low on power. So I guess I'll have to do it this way. Sys_suspend sends a message that says, jump out of the receive loop over to a sys loop, and from there, I'm going to handle system messages, and I'm going to ignore all the other messages. So that way, you can suspend your process, not handle any messages, but still get, I was going to plug in, but I couldn't find a cord. Oh. Sure. So the thing, if you just suspend, you can't receive any messages now. So how would you know when to resume? How would you know what, debugging, how big it is and everything? So sys lets you suspend by giving you an entry point that transfers to the sys receive loop. And that receive loop is crafted to only handle system messages and not process any other messages, so they pile up in the mailbox. And then at some point it says, okay, now you can continue. And you have to implement a system continue function, which puts you back into your original loop. And then you continue on. So it's sort of like trampolining by yourself, I guess.
Did you say that the messages continue to pile up in your queue?
Yes. When you suspend, what you're suspending is the processing that process normally does. And the only thing you're allowing to happen is system messages flow through. And the way system messages flow through, they flow into your receive loop, they go through sys receive loop, and some of them trigger sys to call an API that you've implemented, which is not part of your normal receive loop, which does special functions transferring the data back to sys so that it can give debug messages or format to the screen, trace messages, and things like that. So, and then sys resume puts you back. Here's sys, so sys resume can call system continue, system terminate, or system code change. And normally it would call continue. I suspend, and then I say resume. Resume calls continue. I have to implement in my module where my receive loop is, I have to implement system continue. And basically all it does is what my wait function did. It calls my loop to start again. System terminate gives you a chance to clean up. I suspend, and then boom, the system goes down. Or even I'm just running, my proclub's running, and it goes down. Sys will give me a terminate message, give me a chance to disconnect from the database, clean up my ETS table, whatever. Code change, as Jeff talked about, there's the system suspend, then the code change, then the resume. The code change lets you change any internal state, load some code, whatever, and then continue on. So when a system message arrives, you have to implement a place in your code which calls handle system message. Because you're in your receive loop, and this loop over there wants control. And so you provide an entry point where you say, I'm aware that you want control, and so I'm going to provide you control. Most people don't write that code, and so it's never aware and it doesn't transfer. But if you use Gen Server, that's all built in. It happens automatically. I had to sneak in something. Sys is kind of twisted. It's a bucket of semi-related functions. So there's debugging functions, there's tracing functions, there's suspend and resume. And they're not really related, but they use the same interface, handle system message, for some cases. So I've thrown in my loop this time, debug options. Because in Sys, I can set up multiple debug options at once. That data structure is passed around in my loop, and I have to hand it off to Sys message so that it knows I'm debugging this particular function, and it can print the trace message. So I have to pass this debug options. So inside my receive, I find I've received a system message. I just call handle system message, give it the debug options, and give it that extra parameter that's usually empty. But if you need state external to what system is doing, that's where you have to put it. Then resume or whatever part of the sys will call system continue or system terminate, or code change if I'm doing a code change. Basically, I'm creating a wormhole over to their loop, and then when they're done, they're creating a wormhole back to my loop. It actually doesn't go to my loop, it goes to the API function, and my API function transfers to this loop. But I could do tricky things like, suppose I have two loops. One where I do lots of computation when I have lots of time, but when I get overloaded, I skip a lot of that computation, I just handle messages really quickly. I could use syssuspend, get over here, change my receive loop, sysresume, and I'm back onto this other, faster overload receive loop. Or I could even actually detect that in real time and be able to do that transfer. Debugging. Debugging is a way to insert code into your logic. You have to manually insert the code. This is why it's not as nice as using the Erlang VM, where I didn't think there was going to be a problem ahead of time, and now I need to debug it. This is, I'm working on the code, I can't figure it out, let me go put in code to debug it. So I manually insert sysdebug messages, and I can trigger those through the debug options again. And then I can enable debugging and turn debugging on and off. And they'll either print out to the screen or they'll collect up and I can get them whenever I want. And this same approach is used for tracing, for logging, and for statistics. So that's why I say they're intertwined. If I wanted to just meter how many messages are going through, I would use statistics, but it uses the debug function. Debug is a low overhead method for recording what's happening. Basically, there's a circular buffer, and you tell it, I'm interested in this event and that event and this other event. And it just, whenever it trips over that line of code, it sticks an entry into your buffer. So it's just in memory. It's not logging to disk or sending a message or doing anything. So it should be really fast compared to those other heavier approaches. You won't know anything unless you get that buffer. So you turn on tracing, and after a little while you say, I see the problem. Give me the buffer of the last 10 things that happened or the last 50 things. If you put 10,000 things, you might run out of memory. So you have to be careful what you're putting into the debug buffer. It defaults to 10, so it's supposed to be small, little, quick things. And then you call sys handle debug to do that. Whenever there's a place in your code, like I'm going to send a message, I'll call sys handle debug. I'm going to send a message out. Or I'm going to receive a message. I can call sys handle debug right there. And then when I turn on tracing or logging or debug, I'll get the stuff into my memory queue and I can look at it. You can log to a file. If you do print log, it just prints on the screen. But if you really need the information, you want to call it with a get parameter, and then you get back the buffer and you can squirrel it away and put it in ETS or send a message to somebody else or whatever. So how does sys actually do all this stuff? The way it does it is it installs trace functions onto the debug data structure. So this debug data structure allows you to flag what sorts of things you're interested in. And one of the things is just call this arbitrary function whenever you hit a debug command that I've inserted in the code. And so if I want to get statistics, the sys has a statistics function that it installs automatically. And whenever it trips over the line of code, it calls through that statistics function. But this lets me put an arbitrary function on my debugging, and I can look at the arguments of a call and say, nope, I'm not interested in that one, not interested. Aha, this is the pattern I'm looking for. Log that one aside. And that's very powerful. You can't do that in other languages. But Erlang Trace lets you do that as well. Statistics collection basically just says, you know, I started collecting statistics at this wall clock time. It's now this time, this much time has elapsed. It also gives you any debug events that you've registered, ins and outs, messages coming in and out so you can get message counts. And it also tells you reductions. Reductions are how Erlang does its fair scheduling policy. If I have two processes and I pass control to one process, and let's ignore I/O, normally I would give a time slice to one process and then I would give a time slice to another process. Well, if this process is doing a very heavy computation that takes a long time, and this one is doing a simple process, it may do 1,000 requests and the other one only get through 5 requests. It's not really fair scheduling. So the way it's implemented in the VM is it counts function calls, and every function call is considered a reduction. And so it's like a tick that you've actually made progress. You called a function and a return, and then you called a function and a return. You get so many reductions, and then we transfer it to the next process. So statistics collection lets you see that a process made progress over a given amount of time and messages coming in and out. And then there's getStatus, which was added to Gen servers when they would crash and dump out his crash dump, which I had squirreled away as part of my internal state. So now I have this 18 gigabyte internal state, and it says, I'm crashing. And my internal state was, and it tries to print it all out and crashes the whole node because it's too big. So getStatus was a way for you to put a summary and say, there's an 18 gig memory allocated, and I'm not going to tell you much about it.
I actually forgot to mention that thing in my talk, but if you've ever written handle call get state and return the state of your callback, that is the function that you actually wanted instead, because that works on all Gen processes.
Right. And in my case, I'm using it in my proclub. I have a proclub that has its own state, and it's doing its own receive loop, and I can report the state the way I want to report it. So if you want to dig deeper into it, this stuff's in standard lib in Erlang docs, proclub, and sys. If you go look in the code in the baseline from GitHub, it's actually not that big. It's maybe 800 lines of code or something in each of those modules. Proclub's probably like 400. And then my GitHub, the thing I'm working on right now is called Erlang SP, Erlang Services Platform. It's going to be compatible with OTP, but it's designed to use many, many more processes than you would use with OTP, on the order of 1,000 times as many processes as you would use in a current architecture. And there's examples in the co-op node data receive where I can show this. Right here you can see, if I pull it over a little bit, I've got handle sys, debug co-op, system continue, system terminate, system code change, and format status. So format status, here's a summary that I want when my node crashes or when I send it a message. You can send it a message or call the function getStatus and get back the current state of a proclub. And my system continue, terminate, and code change. You can see system continue. I just jump into my node data loop. All it does is return to my loop. In terminate, I'm just exiting with the same reason I was given so that it's supervisor compatible. And a handle sys is the way system messages flow through my system and I transfer control over to there. So you can poke around that code if you want and see real examples of how it works. Time for questions or no? I blurred through it. I didn't give you enough to actually implement, but I gave you pointers where to look, examples that you can go on GitHub.
You'll have to join us for beer later.
Mm.
We'd like to know how it's used for.
Yeah. I can be available for a little while, but anyway.
Thanks, Jay.
Yep.